Okay, we are continuing with our Chapter 14 video for Strength and Materials. At the end of the last video, we were taking a look at a timber cross-section, and it was 7.5 inches wide, 11.5 inches tall, and we calculated that it had a section modulus of 165.4 inches to the third. Now we are going to use this section modulus in example 14.2. In example 14.2, we are given a simply supported beam with a uniformly distributed load on it. This is a very common loading and support condition. In fact, it is perhaps the most common loading and support condition there is for beams. So the span length of this beam, L, I'll use a script L because just a print L, it's hard to tell is that an L or a 1 or an I. So script L for length equals 16 feet. And the distributed load, which is little w, is 400 pounds per foot rather. So if we want to find the maximum stress, bending stress, that is occurring in this beam, that formula, FB max, is equal to M max over S sub x. So we calculated the section modulus, we know that. What we don't know is what is the maximum moment that is occurring. So how can we find that out? Well, we do know how to make shear and moment diagrams. We could diagram it out in order to find what the maximum moment is. But shear and moment diagrams really only need to be used when you have unusual loading conditions. As I said, a simply supported beam with a uniformly distributed load is extremely common. That is the most common type of beam situation. So if you look in Appendix H in the textbook, what Appendix H does is it shows you a bunch of different beam scenarios, different types of support conditions, different types of loading conditions, and gives you formulas, useful formulas for each of them. So a simply supported beam with a uniformly distributed load is situation number 1, and it tells us that the maximum moment, and it even tells us that it occurs at the center, is equal to the distributed load W times the length of the beam, the span length, squared, divided by 8. So using this formula, I can calculate that the maximum moment is equal to the distributed load of 400 pounds per foot multiplied by the span length of 16 feet squared, don't forget to square it, it's easy to overlook those exponents, divided by 8. So I have a maximum moment of 12,800 pound-feet. Now let's take a moment to think about our units. What we are finding here is a moment. A moment is equal to a force times a distance. So the units are pound-feet. They're not pounds per foot, but pound-feet. Moment units could also be kip-feet, or Newton meters, or kilonewton meters. So we have our unit of force and our unit of distance. The unit of distance is what we have to be careful about. We are going to take this moment value and plug it into this formula, which is the maximum moment divided by section modulus. The units for section modulus are in inches to the third power, not feet to the third power. So we're going to have to convert these units to make them usable. And it's easier to convert the moment units to inches than it is the section modulus into feet. At least I think so. So this moment, maximum moment now, is going to now become 12,800 pound-feet multiplied by, and this is why I want to point out, is pound times feet, not pounds per foot. So we're going to be multiplying by 1 foot below 12 inches. So for every 12 inches, that's equal to 1 foot. So in other words, we're multiplying by 12, not dividing by 12. So 12,800 times 12 is equal to 153,600, and now my units are in pound inches. So now I can take this and plug it into my maximum bending stress formula. FB max is equal to the maximum moment of 153,600 pound inches divided by my section modulus was 165.4 inches to the third. .4 inches to the third. And so that's going to equal 929. And again, if we look at our units, we have inches over inches to the third. So it's like inches to the first power divided by inches to the third power. This will cancel out two of these, or I'm sorry, one of them, and leave two of them behind, inches to the second power. So I've still got my pounds up top, and now inches on the bottom. Pounds per square inches is PSI. 929 PSI is the maximum bending stress in this beam.